1969 marked a significant moment in the evolution of holography, a field Dennis Gabor had pioneered nearly 2 decades earlier. Gabor's 1969 work, Microscopy by Reconstructed Wavefronts, served not merely as a retrospective, but as a considered analysis of the limitations of his initial invention and the transformative developments that followed. The genesis of Gabor's endeavor lay in the inherent limitations of 1940s electron microscopy. Spherical aberrations in the magnetic lenses employed caused a significant reduction in resolution, primarily stemming from the loss of phase information during image formation. Gabor's solution was elegant in its conception, though initially flawed in its execution. He proposed a 2-stage process. First, the interference pattern between a coherent reference wave and the object wave was recorded. This interference pattern mathematically manifests as an intensity equation I equals the absolute value squared of R plus O, which expands to the absolute value squared of R plus the absolute value squared of O plus R star O plus R O star. The latter 2 terms, involving the complex conjugate, represent the crucial phase information, complete wavefront encoding. This recording, the hologram, effectively captured the phase information lost in conventional microscopy. The second stage involved illuminating the recorded hologram. The plate, acting as a diffraction grating, reconstructs the original wavefront, revealing the microscopic object with enhanced resolution. A critical technical point emerges here. Gabor's initial method, an inline approach, employed a reference wave propagating along the same axis as the object wave. This resulted in the production of a conjugate wave, generating a superimposed, blurry twin image, severely compromising image quality. This twin image, an autofocus replica of the desired image, proved a major obstacle to his early holography. The fundamental concept, however, held remarkable promise. Gabor's own early holograms of microscopic diatoms served as a compelling demonstration of both the potential and the limitations of his initial method. These tangible results highlighted the inherent promise despite the significant resolution issues presented by the twin image. Gabor's ideas were demonstrably influenced by existing work. W.L. Bragg's conception of an X-ray microscope, seeking to circumvent limitations of visible light microscopy, offered a conceptual precedent, highlighting the desire for enhanced resolution in microscopy. Further, F. Zernig's phase contrast microscopy, a technique to enhance contrast of transparent objects by manipulating phase shifts, provided a concrete example of a successful strategy in addressing similar imaging challenges, manipulating phase information to improve contrast and resolution. These influences underscore the intellectual climate driving Gabor's innovation. The period between Gabor's initial invention and his 1969 paper witnessed a substantial transformation in the field of holography. The advent of the laser in 1960 provided the first practical source of highly coherent light, a pivotal development that had been absent from Gabor's earliest efforts. This facilitated the critical breakthrough of off-axis holography by Leith and Upatnieks 196,264. Leith and Upatnieks' method cleverly introduced the reference beam at an angle relative to the object beam. This solved Gabor's twin image problem by spatially separating the real, virtual, and serial reconstructions, resulting in high-quality holograms without the blurring of the conjugate image. Gabor's 1969 paper, therefore, acts as a thoughtful reflection on a field he had initiated but that had been significantly advanced by others. It provides perspective on the evolution of holography leading up to his 1971 Nobel Prize. The direct influence of Gabor's work is evident in the contributions of Leith, Upatnieks, and Dennis Gabor volume holography, all of whom built upon his foundational concepts. The impact of Gabor's work extends far beyond these immediate successors. The principle of wavefront reconstruction lies at the core of numerous technological descendants, including holographic interferometry for non-destructive testing, holographic data storage, and security applications, alongside its conceptual offspring such as computational phase retrieval and adaptive optics in astronomy. The story of Gabor's holography offers a compelling narrative arc, a method conceived to overcome the limitations of a specific technology. Electron microscopy unexpectedly paved the way for a completely new field within optics. This profound irony underscores the unpredictable, often serendipitous, nature of scientific progress, a testament to the enduring intellectual impact of Gabor's original vision. The ultimate legacy of Gabor's work, thus, surpasses the original intent, demonstrating the true power of foundational innovation. For over a decade, Gabor's invention remained a solution of profound elegance awaiting a problem it could practically solve. The principle of wavefront reconstruction was sound, yet its physical realization was perpetually compromised by the limitations of available light sources. The twin image problem, an intrinsic mathematical consequence of his inline recording geometry, relegated holography to a state of tantalizing potential. This period of quiet incubation ended abruptly with the advent of a technology from an entirely different domain of physics. In 1960, the invention of the laser furnished the exact tool Gabor's method required from its inception, a source of light possessing extraordinary spatial and temporal coherence. The laser's beam was a nearly perfect plane wave, a physical manifestation of the idealized reference wave in Gabor's equations, and its arrival catalyzed the transformation of holography from a niche microscopic technique into a revolutionary optical science. The critical breakthrough was achieved by Leith and Upatnieks at the University of Michigan between 1962 and 1964, drawing upon their experience with synthetic aperture radar, which shares a deep mathematical formalism with holography. They devised the ophaxis recording technique. Their innovation was conceptually simple yet transformative in its effect. They introduced the reference beam at a distinct angle to the object beam. This angular separation encoded the phase information onto a high-frequency spatial carrier, essentially modulating the interference pattern on the photographic plate. Upon illuminating this developed plate, the hologram now behaved as a complex diffraction grating. The reconstructed light separated into distinct orders, angularly displaced from one another. The zero-order beam, the undiffracted background light, passed straight through. The first-order diffracted beam formed a perfect virtual image, completely free of its conjugate twin. The minus first-order beam formed the real image, also spatially isolated. The twin image problem was thereby eliminated. Leith and Upatnieks had physically separated the overlapping mathematical solutions that had plagued Gabor's original scheme, unlocking the full potential for creating visually spectacular, three-dimensional images. Gabor's 1969 paper, Microscopy by Reconstructed Wavefronts, serves as a magisterial reflection on this transformed field. Authored just 2 years before he would receive the Nobel Prize in Physics for his discovery, the work is a testament from a founder witnessing his creation flourish in ways he could have scarcely imagined. He analyzes with scholarly precision the developments catalyzed by the laser and the ophaxis method, acknowledging their roles in solving the primary obstacles that had constrained his initial efforts. The paper is the perspective of an intellectual originator providing a comprehensive overview of a discipline that had now fully come of age, a discipline built upon his foundational insight but carried to maturity by the ingenuity of the direct influence of Gabor's principle is a clear lineage of scientific succession. Leith and Upatnieks explicitly built their ophaxis method upon his published framework. Concurrently in the Soviet Union, Dennis Gabor developed volume holography, a technique that records interference patterns throughout the thick emulsion of a photographic plate, creating brilliantly colored reflection holograms. Dennis Gabor, too, recognized his work as an extension of Gabor's fundamental concept of wavefront reconstruction. The ultimate legacy of holography extends far beyond these immediate successes, branching into a vast conceptual and technological tree. The core principle of recording and reconstructing a complete optical field has become a foundational tool. Holographic interferometry, for instance, enables non-destructive testing with breathtaking precision. By superimposing two holograms of an object taken moments apart, any microscopic deformation, stress, or vibration becomes visible as a contour map of interference fringes, revealing hidden flaws in materials. Holographic data storage exploits the volume of a recording medium, stacking terabytes of information in a small crystal by multiplexing holograms at different angles. Its most visible application resides in security, where the difficulty of replicating a complex hologram provides a robust defense against forgery on currency and credit cards. Conceptually, the idea of capturing phase from intensity measurements has spawned purely computational descendants. Algorithms for phase retrieval in fields like X-ray crystallography owe an intellectual debt to Gabor's physical method. Perhaps its most dynamic legacy is in adaptive optics for astronomy. A telescope's wavefront sensor measures the real-time distortion of starlight caused by atmospheric turbulence. A computer then calculates the precise conjugate wavefront needed for correction, which a deformable mirror physically generates, cancelling the distortion. Is a ReHIM, closed-loop holographic process, allowing ground-based instruments to achieve clarity rivaling those in the trajectory of Gabor's work presents a magnificent irony of scientific discovery, a method conceived with the singular purpose of correcting the aberrations in electron microscope lenses to push imaging toward the atomic scale, instead gave birth to an entirely new paradigm in optics. Its ultimate legacy was a comprehensive science and technology of three-dimensional light, a contribution far grander and more versatile than its specific, intended application. This outcome is a powerful illustration of fundamental research, where the pursuit of a focused problem can yield solutions that transcend their original context, reshaping our very ability see and record the world,